All right, good afternoon to anybody who's watching. My name is Max Daughtry, and for my mechanics project, I did examining the loss in total mechanical energy due to drag of a spherical projectile. So the problem that I set up was to consider a projectile under the influence of both linear and quadratic drag forces, as well as gravity at SCP, and we want to calculate the difference in the total mechanical energy between the projectile that does not experience drag and the one that does experience drag. Um, but it's the final total mechanical energy, so all the way at the end of the trajectory, we want to calculate the difference in mechanical energy, and that difference will actually be the energy lost due to the drag force. Um, yeah. So for the analytical solution, I wanted to define XY coordinate axes with origin at ground level and Y pointing straight down, so that force was pointing in the direction of motion, and or gravity, the force of gravity was pointing in the direction of motion, and the drag forces opposed the force of gravity. So, um, and X pointing in the to the right. So to define the initial conditions or the initial values, we'll say. We set y naught equal to 100 meters, so the initial y position is 100 meters above the ground. Initial x position is at 0 meters. The initial y velocity was 0 meters per second. The initial x velocity is 5 meters per second. The mass of the projectile is 10 kilograms, and the coefficient of linear drag is 0.00016 newton seconds per meter squared, and gamma, the coefficient of quadratic drag, is 0.25 newton seconds per meter to the fourth. So given all these initial values and what we defined up here, we can set up the equation of motion, which gives us this force vector. So the force is equal to the gravitational force minus the quadratic drag force minus the linear drag force. And right off the bat, we can notice that v hat is equal to vector v over the magnitude of v, which reduces our equation to this, which is a bit easier to work with. And I think the first and most obvious approximation that we can make is to neglect linear air resistance. So doing so just completely gets rid of this term over here, and then we can break it up into the y and x components as well in the same step, which gives us the force in the y direction, which is force of gravity minus the quadratic drag, and then force in the x direction, which is just the quadratic drag. And then the second approximation we're going to make is considering that Vy squared for most of the trajectory is much greater than Vx squared. We're going to approximate that Vx squared plus Vy squared is about Vy squared. And I confirmed the validity of this approximation using the numerical results I got. So I have the graph of that at the bottom here. So we can see that for most of the trajectory, Vx squared plus Vy squared is pretty close to Vy squared. And it turns out it is actually a very good approximation. So this approximation ultimately gives us that the force in the y direction is the force of gravity minus this quadratic drag, and then the force in the x direction is as follows. So first we're going to start with the solving for the position in the y direction and the velocity in the y direction. So we're going to start with this equation of motion, which is just an ordinary differential equation. Plugging it into Wolfram alpha will give you this right here with two constants of integration. And then we can take the time derivative of this equation, which will give us the velocity in the y direction and only one constant of integration. Then we can plug in our initial conditions. So at time t equals 0, we expect the velocity in the y direction to be 0. And so that leaves us with a constant k1 equaling 0. Going back to our equation of position and plugging in k1 equals 0. And then at time t equals 0, we want the y position to be 100. All this together, we get this equation here, solving for k2, which leaves us with, because the natural log of 1 is 0, k2 equals 100. So altogether, in the y direction, we have our position stated here and our velocity stated here. Next, we move on to the x position and x velocity. So starting with our equation of motion, and then dividing by m, and then also substituting in our y velocity, and then multiplying by our x dot from here. So what I did when solving this and plugging it into Wolfram Alpha is instead of x double dot, I just said v dot, and then instead of x dot, I just put v. This makes it a first order differential equation instead of a second order differential equation, which obviously makes it a bit easier to get a result for, which gives us our velocity in the x direction. Plugging in our initial conditions that at time t equals 0, the x velocity is 5 meters per second, we get that c1 equals 5. Integrating this, we get that the x position is shown here with one constant of integration. Plugging in our initial conditions that x at t equals 0 is 0 gives us that k1 is equal to 0. So altogether, we get that the x position is given by this equation and the x velocity is given by this equation. Finding the kinetic and potential energies is pretty straightforward. You just have to plug in the x velocity and y velocity into the equation 1/2 mv squared, which is just the equation for kinetic energy. So doing so gives us this equation. The potential energy is just, of course, mg times the position above the ground. So plugging in our y equation from up here into this potential energy equation, we get this equation here. The total mechanical energy will then be T plus U, and then there will be some energy lost to drag. I didn't include it here, but there is some energy lost to drag here, which is what we're ultimately trying to find. So we get this 1/2 m blah 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 blah, which is just the kinetic energy plus the potential energy. And then finally, to find the energy at the end of the trajectory, we need to find where y is equal to 0, or what time y is equal to 0. So all we have to do is just find where y equals 0 and then solve for t, which gives us this expression here. Everything here is a defined function or a constant. Therefore, we get 6.4477 seconds. So plugging 6.4477 into our equation for energy, we get energy at the end of the trajectory is 1,947.67 joules. Now, calculating the total mechanical energy of the particle without drag is just a basic physics 1 problem, so I'm not really going to go through my thinking there. I'm just going to say total potential energy gives us at the end of the trajectory is 9,925 joules, which we expect to be constant, so we don't have to find where y is equal to 0. And then taking the difference between the energy of the projectile without drag and the energy of the projectile with drag gives us 7,977.33 joules. So that's our analytical answer, or answer derived from our analytical solution. So now we're going to move on to the numerical solution. So at the beginning, we need to define all of our constants, physical constants, and then we need to set up our initial values for x, y, dx, dy. And then these are my functions for force, kinetic energy, and potential energy. Um, and then this calculates, it has a bunch of arrays that will be appended to while over a loop, the loop goes until the y position is less than or equal to 0. Through each loop, it calculates the various quantities, so kinetic energy, potential energy, total energy, acceleration, velocity, position, um, and appends these values to a list, except for acceleration, because we don't really need that in the end. And then this was with drag. This code block is the same thing here, but without drag. I didn't call the linear drag or the drag force function because we don't care about that in this code block. So the only force is gravity. That's why AY is just negative G. And then we move on to this is just where our just putting the equations that we found all the way at the beginning and putting it into code so that we can analyze it alongside our numerical solution. So it's just our y equation, x equation, vy equation, vx equation. And then here, this is for with drag. This is for without drag. Again, just the analytical solutions. Nothing's happening here that isn't just crunching numbers, basically. So now we can start comparing the analytical to numerical solutions. So we see the trajectories here. So the numerical solution with drag gives us this blue line here, and then the analytical solution with drag gives us this red line here. So we see the trajectories at the end are not that close together, but when we're looking at the energies, they'll be a lot closer. The lines will be a lot closer together when we're just looking at energies. And then, of course, for the without drag, we expect the analytical and numerical solution to be pretty much exactly the same because no approximations we're taking. They should just be doing the exact same thing, which they are. So now we can start analyzing the energies with respect to time. So these two lines right here are our mechanical energies, our total mechanical energies. And so the cyan line is our analytical solution. And then the black line is our numerical solution, and they are very close together. And that follows with our potential energies here, where the red line is our analytical solution and the blue is our numerical. And then these purple and green lines here, which are our kinetic energies. And everything makes sense. Potential energy is 0 at the end of the trajectory, which we would expect because it's on the ground. Our kinetic energy is equal to our total energy, which we would expect since we haven't really accounted for the energy loss to drag. That's not in our equation really. So we expect all the mechanical energy to be kinetic energy. So moving on, this is where we find the difference for the numerical solution between the energy at the end without drag and then the energy with drag. Take the difference of them, we get 7,978.76 joules, which is very close to what we got up here, 7,977.33 joules. So just a few joules off, really. And then here we do basically the same thing we did up at the top at the end, where we get 7,976.89 joules. So the only reason that the analytical solution here is different from the analytical solution we got at the top is because we're not, the dt, the change in time, the time interval is not approaching 0. It's a finite amount, so it's not going to be perfect. And then just to further set in the fact that it's a very good approximation, we find the percent difference between our analytical and numerical solutions, and we see it's 0.023% different when it comes to the energies. So it is a very good approximation when it comes to finding energies. And then we have our motivation for the Vy squared is approximately Vx squared plus Vy squared. So yes, that was my project. Thank you very much for watching. All right, have a good day.